Prerna ma'am, you are muted.
Okay, okay. Now you can listen me. Good afternoon, sir.
Yes,
So
yes,
shall I
I
start?
can hear you. Yeah, please go ahead, ma'am.
Okay. Good afternoon, everyone, and welcome to today's webinar on the occasion of Pi Approximation Day. My name is Prerna Jain, and I will be your host for this session on the behalf of Department of First Year Engineering and Technology, Pimpri Chinchwad University. Before we get started, I would like to request all participants will be muted during the presentation to minimize background noise. And if you have any questions, then please type them in the question answer section. Now, it's my pleasure to introduce our distinguished speaker, Mr. Himanshu Vaidya. Today, we are honored to have Mr. Himanshu Vaidya with us. He is a founder and CEO of eQspanse's Next Generation Technologies Private Limited, with over the 6 years of work experience in big data and AI. He has made significant contributions in big data, machine learning, mathematical modeling, and many more fields of AI since 2007. Mr. Himanshu Vaidya holds a bachelor's in computer science from University of Pune, MSc in space sciences with the specialization in astronomy and astrophysics from the Department of Space Sciences, University of Pune. Postgraduate Diploma in Advanced Computing, Center for the Development in Advanced Computing, and currently he is pursuing his PhD in Quantum AI applied to astrophysics and cosmology from Christ University. He received awards in excellence and innovation of AI education. He also received an award for the All India Council for Robotics and Automation in the Global Artificial Intelligence Summit. Today, Mr. Himanshu Vaidya will be sharing insights on the role of mathematics in quantum computing, AI, algorithms, and applications. This session promises to be highly informative and engaging, and I am confident we will all come away with the valuable knowledge and perspectives. Please join me in welcoming Mr. Himanshu Vaidya. Now, I hand over to Mr. Vedya for the wonderful session we all waiting for. Sir, please. Welcome, sir.
Thank you, ma'am. Thanks a lot to Prerna ma'am, Mahesh sir, and Pimpri Chinchwad University for providing me this opportunity to share my understanding. And with the due interest of time, I would quickly start my session. So let me quickly share my screen. Yeah, I'm able to share. Just let me know once everyone is able to see my screen.
Yes, it's visible.
Okay. Okay. So thank you, everyone. So just change the perfect. Okay. So, so today, on the occasion of Pi Approximation Day, because today is 20th of July, which is like the best integer approximation of the irrational number pi, which is one of the most famous constants. So basically, the irrational number, which is more famous than any other irrational numbers like E and others. So, so, so this is the first, I would say, irrational number probably discovered by mankind, and it is defined as the ratio of the circumference. So it is the ratio of the circumference to the diameter of a circle. And this particular number is an irrational number, so which means that it is if represented in decimals. Okay, so 3.14. So, somebody's speaking. So let me just check. Yeah, sure.
पण ते वेगळं असेल ना, आता सिलेबस बदलला असेल.
So, Mahesh sir, if you can just please check
Yes.
who is speaking.
Shilpa Lad madam, please mute yourself. Shilpa Lad madam. Shilpa Lad, please mute yourself.
Yeah, okay, thanks a lot, sir. So, so this is a number where you can never get any repetitions after the decimal point. Okay, so that's the definition of an irrational number, and that is one of the main reason that if you have a recurring decimal, you can represent it in the form of p by q, where both p and q are integers, and that is the definition of a rational number, while an irrational number is a one which can never have a recurring decimal. As a result, if you calculate the correct value of pi, you will never get it, because continuously the decimals keep on adding to the right side of the decimal point. And that is exactly where many algorithms have been written by great experts. Now, with the advent of computers, we have also utilized big data and AI technologies, supercomputers, high performance computing clusters to calculate pi to maximum decimal digits of accuracy. And if you Google, you will find that there are, let's say, 1,000 digit, then 1 billion digit, then 1 trillion digit. Till that particular point, we have found out the accuracy of this particular constant. And there are quantum algorithms also which can be used to estimate the correct value of pi. So with this, by honoring pi as the irrational number that has contributed a lot in our understanding about this world. Secondly, one of the main discoveries of mankind, one was called as fire. The second one was basically invention of a wheel. So invention of wheel has a lot to do with the invention of circle. So when man started, so that is human beings, Homo sapiens, discovered that yes, this is circle. It was always a problem to correctly find out what is a circle and then to identify its circumference correctly. So I think this problem of understanding the nature of pi and its applications across various different domains is quite fascinating to the mathematics community, as well as all the engineering, as well as other scientific communities across the world. If we know that Euler's identity, basically we have this identity where both the square root of -1, that is I, and then E, which is another irrational number, and pi, all actually play a significant role in one single equation. Okay, so we know that these kind of fascinating things exist in the area of mathematics. And as we truly call, some mathematicians say that mathematics is the queen of all sciences and king of all arts. So with a great tribute to mathematics as a discipline, the contribution of mathematics in shaping science, technology, and the future of mankind, I think let's start to this session where I would be covering um, the role of mathematics in some of the most advanced disciplines that we know today. And most of you must already be knowing artificial intelligence. There is a lot of boom regarding AI across the world, but quantum computing is another disruptive technology that is contributing a lot to shaping up the emerging and next generation technology future. So from that perspective, let's quickly move to the next slide. So introduction to quantum computing. If we all know what is quantum computing, so I would quickly like to cover up. Basically, quantum computing is that discipline which uses quantum physics or quantum mechanical phenomena to do computation. And if we go towards the history of computers, then again, by the way, computer science is an advanced discipline of mathematics, the theoretical computer science, at least the automata theory. And we had mechanical computers, then analog computers, digital computers, and then electronic computers came after that, when we could actually embed logic into smaller and smaller space called as circuits, and then more circuits got integrated called as large scale integration inside chips, and then VLSI came into existence, which is called as very large scale integration, which actually revolutionized the way we started doing computations. So initial days calculators to modern day supercomputers, that has been a fantastic journey for all classical computing fans. And um, Richard Feynman, who is one of the greatest professors in physics, who is very famous for his lectures called as Feynman lectures in physics, he was the first to actually coin up that yes, quantum mechanics and quantum physics related phenomenon can also be used to do computations. Okay, so if you can use a mechanical computer, basically it is for analog systems. So mechanical devices or systems can do some computation, and we know abacus. Then there is a digital version of mechanical devices like abacus and all. But from mechanical to electrical to electronic to quantum is the current revolution, and the analog computers are coming back into picture, which earlier used to be using mechanical systems, but now today we are using quantum systems for doing analog computations. When we say analog computations, it is basically your input variable is analog versus digital. So for example, if data is discrete, then what we should do, and if data is analog, then what we should do. In these particular um, 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 different types of concepts represent the data. And from that perspective, statistics plays an important role here, because in statistics, we must have learned about different types of variables, continuous versus discrete. So whenever we talk about any technology or any scientific discipline, the most important thing here is that what are the fundamental sciences that we need to consider. For quantum computing, artificial intelligence, and associated algorithms and applications, I strongly feel that mathematics, physics, as well as advanced algorithm development has a lot to do in making these disciplines successful, and the applications are significant. So I will not go into the technical details in this session, but I'm just sharing some of the slides that fundamental building block of quantum computation is basically qubit. If you have two states superimposed, that is 0 and 1, it is called as qubit. If it is 3 states, then it is qubit. And if it is 4 states, it is called as q-quartz. And then if it is more than 3, 4, n states superimposed for simulating a qubit, it is basically called as qubit. So why quantum computers are used is basically for their speed, for simulation, for complexity that they represent. And then there are several challenges as well, like noise, fidelity, and scale and commoditization. For example, scale out of quantum computing hardware mainstream is currently one of the challenges. Now let's move to the next slide, where we are defining quantum computing. So basically, quantum computer is a type of computing that studies the non-classical model of computation. Now, when we talk about non-classical model of computation, again, we have to go back to something called as complexity theory, which is classical complexity theory and then quantum complexity theory. These are some of the disciplines. If you know Massachusetts Institute of Technology, they have their open courseware. So if you go and search quantum complexity theory, they have launched a free course on quantum complexity theory. But if you go and look into the details of those courses, you will understand that it is inherently talking about a lot of problem domains, and for which you need mathematics and you need to understand a lot of details about problem domains. So for example, they talk about problem spaces, then you talk about the sets of problems. And we computer science students know that there is something called as P versus NP, which is a $1 million price problem today. Similarly, there are so many disciplines which can never go ahead without the background of mathematics going into picture. In a similar fashion, quantum information processing is a particular discipline which involves this particular thing called as quantum complexity theory. So I'm not going into the details of how it is done, but this is just to create an awareness that yes, quantum computing, artificial intelligence are some of the great disciplines that are causing disruption in industry and high-end academic research today. And we must understand that there is a lot of fundamental mathematics and physics and technology that is going to make applications for industry using these particular fields. So what is a quantum computer? Basically, there are various approaches to build this kind of quantum computer. So as we studied that, unlike bit, which stores either 0 or 1, in quantum computer, we have the fundamental building block called as qubit, which has 0 and 1 superimposed on each other. This particular representation is called as block sphere representation of a qubit. So, and anything that is used to simulate a qubit will follow this particular mathematical representation, which means that on the surface of the block sphere, there are infinitely many pure states of a qubit. Below the surface, that is from center to the surface, all impure states are there. So accordingly, even to describe the fundamental building block of quantum computation, you need to have a mathematical background. And again, this block sphere is basically representing complex numbers, since it is in complex domain. So which means that to understand quantum computing, we need to have a background in complex number mathematics, and then algebra as well as associated geometry, then linear algebra, as well as certain other disciplines like statistics and advanced statistics to understand machine learning and AI aspects of quantum artificial intelligence. So when we talk about this particular equation, this is basically a wave function. So wave function is providing us information about subatomic scale phenomena. So what is quantum computer? Then Feynman said that we can use quantum physics related phenomenon. What is quantum physics? It is the theory that provides us explanation about the microscale nature of our universe that we live in, which means that the way atom and subatomic particle level universe actually is explained, it is all using the quantum mechanics laws. And this particular theory has provided maximum applications till date from past more than 100 years now. And it was a theory for which Einstein also got his Nobel Prize. By the way, so many people mistake that Einstein got Nobel Prize for relativity, but actually Einstein did not get a Nobel Prize for special or general theory of relativity, for which he is world famous. Rather, he received Nobel Prize for providing a successful explanation of photoelectric effect, which is a quantum mechanical phenomenon, which talks about that light is also a particle, like it is also a wave. In similar fashion, so every subatomic scale particle actually has both wave and particle nature. It has uncertainty inherently embedded into its explanation, especially given by Heisenberg's uncertainty principle. So likewise, to understand quantum physics, you need to have a background in physics, especially to study subatomic scale universe. In a similar fashion, to describe these phenomena, you need to understand probability and statistics, linear algebra, Hilbert spaces, and similar type of such disciplines. So the right-hand side wheel, if everyone can see this, this describes that there are multiple types of quantum physics related phenomena that are used to simulate a qubit. And based on the type of technology in which quantum physics and engineering is used to create a quantum computing hardware and its fundamental building block of a qubit, we can see that superconducting loop is one of the type of technology. Then trapped ion is another type of technology. Then photonic quantum qubits. So photonic qubits is another technology. Then spin quantum dot. cold neutral atom or helium atom, then NV diamond, adiabatic annealing, as well as topological quantum computers. All these different types of systems talk about different properties of quantum mechanics or quantum physics phenomena to create the single basic building block of quantum hardware called as qubit. Now, when we compare between bit and qubit, it states that we have two possible states, that either 0 or 1. Then basically, when we talk about bit versus qubit, there are three different analogies or angles in which we must think. One is how we physically represent a bit versus how we physically represent a qubit. Then how we logically represent a bit versus how we logically represent a qubit. And the third most important angle is how we mathematically represent a bit versus how we mathematically represent a qubit. And that is exactly where the geometric interpretation I showed earlier, which is this block sphere. And then we have to build, when we say quantum software programming from this qubit level, we have to understand the mathematics behind a qubit. Then if there are more than one qubits, then how will you use them to create multi-qubit systems? How these multi-qubit systems and respective operators operate on them. And for this, there is a whole lot of linear algebra, Hilbert spaces that one needs to study. And once you apply these gates, which are essentially matrices applied on unit vectors, or let's say column vectors, which represent qubits, then um, we construct something called as a quantum circuit. And then using this quantum circuit, we have to further build on top of it to develop quantum algorithms. So essentially, and these quantum algorithms can be then embedded as modules in quantum software programs and utilized to develop more sophisticated quantum software programs. So essentially, quantum software programming means that it needs algorithms, that is quantum algorithms. They need quantum circuits, and quantum circuits need multi-qubit systems and operators operating on those multi-qubit systems. And this all has a solid mathematical foundation of linear algebra, Hilbert spaces, and to some extent probability. Now, when we say quantum, why the whole world is behind quantum computing? We all know that everybody is behind AI, but globally, if you see, people are less aware in India, but in globally, if you see that so many companies and lots of different governments are actually developing quantum computing hardware, and so many software companies have been formed to develop quantum software, because there is a huge opportunity, $1 billion and eventually $1 trillion opportunity in quantum computing, artificial intelligence, and a combination of quantum computing and artificial intelligence called as quantum machine learning or quantum AI. When people started developing quantum algorithms, Peter Shor, who received Nobel Prize a couple of years back, is famous for his Shor's algorithm, one of the most famous algorithms in quantum computing. And this algorithm solves the integer factorization problem very, very quickly as compared to the classical computing counterparts. And that is where Shor's algorithm poses a great threat to all of the encryption schemes today. So the most of the systems across the world which communicate data are based on RSA encryption. And RSA encryption is a great threat for quantum computing algorithms. Basically, quantum algorithms pose a threat to RSA encryptions. So if we get a mainstream quantum computer of 1 million qubits, let's say 1 year, 5 year, 10 year down the line, then definitely basic Shor's algorithm implemented on a large scale quantum computer can easily break any of the security mechanism, information security across the planet. And that's why most of the aerospace defense companies, all governments, as well as large banks and insurance companies are all behind developing quantum computing capability and quantum technology capability so that they can secure their data. And as quantum algorithms pose a threat, the solution is also quantum. Quantum that particular subdiscipline of quantum computing is called as post-quantum cryptography, where based on quantum key distribution protocol and several other methods, you develop and encrypt the data in such a fashion that it cannot be broken even by the best quantum algorithms. So what essentially is meant by developing a quantum technology is that I'm talking about the software side. So basically, if someone develops a method in quantum, then if that method beats all classical methods, if the answer is no, then you have to go back and do research and work on your quantum algorithm. If the answer to this question is yes, then that terminology in the quantum community is called as limited quantum speedup. If um, somebody is working, let's say Google or NASA, and they beat all classical methods, then that particular level is called as quantum advantage. And then if your performance is so much better that it would be crazy to do it without a quantum computer, which means that the billions of dollars invested are paying you back, then that is called as quantum supremacy. So the claims of quantum supremacy were done by NASA and Google in 2019, but when the research community evaluated, they found out that um, it was still not a quantum supremacy case. Okay, it was not a scalable, programmable way in which they claimed it. And then China claimed it again after an year or so, and then again it was validated by the research community, and it was found out that it was maybe quantum advantage but not quantum supremacy. And then Xanadu, I think in 2021, used photonic quantum computing hardware. The other two used superconducting qubits, quantum hardware. And then Xanadu claimed that, yes, they achieved quantum advantage using photonic quantum computing algorithm called based on Gaussian boson sampling. So it's a very specific method. And it was found out that, yes, Xanadu has achieved it, but again, it is not scalable. So which means that players like Google, NASA, Xanadu, Chinese researchers, several big universities are behind this particular technology. There is high risk but high reward in this particular technology stack. What are the applications of this particular technology is basically into quantum simulation, quantum machine learning, quantum optimization, and other algorithms. So for example, all route optimization and map related optimization problems, actually quantum optimization plays a vital role. And again, you have to understand a lot about quantum complexity theory and then understand the mathematics behind it in order to develop something that can go as an industry application in this particular area. Now, scientific domains for learning quantum tech. So basically these are, and again, I'm talking on quantum, I will also shift on AI. So there are different concepts in physics, mathematics, human sciences, computer sciences, and engineering that actually play a vital role in describing and learning quantum technologies. So again, you can see that linear algebra, groups theory, okay, analysis, okay, formal real analysis, complex analysis, and complexity theories are some of the major disciplines that one needs to learn in order to understand quantum computing and eventually quantum machine learning. Probability statistics and other disciplines play a vital role. And of course, Fourier transform, which I will come to. So Fourier series, Fourier transform, Laplace transform, wavelet transform, etc. also play a vital role in doing a lot of data analysis problems. Then relation between different topics in quantum technologies is actually mentioned here, which is just to provide you a sense that there are within quantum technologies, quantum sensing, quantum communication and cryptography, then quantum computing business solutions, then quantum software development tools, quantum computing engineering, quantum enabling technologies, quantum computers per qubit type, then linear algebra, gate-based analog quantum computing, then quantum algorithms and different complexity theories play a vital role. And all this has a strong physics based, then mathematics, then engineering, physics and engineering combined, and then geopolitics and societal impact to make sure that quantum technologies are spread around the world and quantum technologies are benefiting the society. Then quantum physics to quantum technologies, basically, this is something right from starting to qubit basics to use case assessments to quantum algorithms to error correction to measurement-based quantum computing, etc., etc. And you can see the amount of mathematics that has been described in Bell equalities as well as Schrodinger equation, etc. For complexity theories, this is basically description of sets. All these different things that are explained here is sets. Then again, linear algebra. So the long story short, the crux of the matter is basically that this is a multidisciplinary field, and mathematics is playing a vital role in making sure that we understand and we develop industry grade applications in this field. So this talks about the first and second quantum revolution, where in the first quantum revolution, from past 100 years, so many scientists actually developed great discoveries, especially related to manipulation of group of quantum particles, that is photon, electrons, and atom interactions, which actually led to transistors, lasers, fiber optics, GPS, photovoltaic cells, atom clocks, etc. So all these applications were because of the initial technology, that is 1947, post 1947, which started getting mainstream. Post 1982 is the era of quantum computing, quantum telecommunications, quantum cryptography, and quantum sensing, where the scientific community started developing technologies that were capable of manipulating superposition and entanglement on individual particles. Now, computing paradigms, as I earlier also discussed, that based on different types of mechanisms, we have different types of computational paradigms. Who is into this game? So here we saw that there are various types of ways in which we can develop a general computer. For quantum computers, we have these many different ways in which we can develop it. For example, mechanical, electronic, quantum, and quantum contains these many different types, and nature inspired biological analogs which contain these ones. Now going back to what about these computing paradigms, how they are used in quantum um, uh, computation. So there is something called as classical computers, but you have quantum inspired algorithms, then quantum emulators. Then these are the players who are working on this: Microsoft, Multiverse, Zapata AI. Then again here Microsoft is there, here Google is there in this particular domain. Google is also into gate-based quantum computers, mostly in the NISQ era. PsiQuantum, Alice and Bob and Microsoft are into fault-tolerant quantum computers, technologies, etc., etc., etc. So this is where we can see that so many big players are actually have already entered into the game from past 2-3 decades, IBM being ahead of the curve. So I have myself been using IBM quantum computing hardware from past 7 years, and Google, Amazon, Microsoft based hardwares, Xanadu, which I mentioned earlier, from past 4 years. Then, so I talked something about in the basic definition of quantum computer, which was about models of computation. So models of computation has a lot to do with understanding of some of the complexity theories, and then NPP. So this is again, we boil down to mathematics. And if you see here that what all different things come into picture is that not theoretic problems can be solved using topological quantum computers, optimization problems can be solved using adiabatic quantum computers, etc. So this is basically the model, adiabatic model of computation, topological quantum computing, and that respective model of quantum computation, etc. Again, to explain, this is something which we saw earlier, but this is expanded form of it. Basically, different types of problems and which problems fall under which domain is explained in this particular side, where you have P-space. For example, the game of chess or Go actually falls in under P-space type of problems. Then computing the permanent of a matrix falls under hash P complete. NP-hard problems are finding optimal path in a graph, map coloring, or theorems demonstration, etc., etc. So if you talk about what we do using quantum algorithms or AI algorithms and quantum machine learning, quantum AI algorithms to solve real life problems of route optimization. Okay, then finding out patterns in DNA sequence, drug discovery, etc., or some aerospace related problems. All these things you have to finally actually simplify it and represent it into a mathematical problem. And that is exactly where I wanted to emphasize today on the basis of Pi approximation day, that there is a lot of things going in the background that utilize the fundamental mathematics into picture in order to implement the solution of these problem domains. So any questions so far? Okay, I will quickly go to so this is again the same thing which I have described earlier. It's just a revision. What we studied is basically superposition and entanglement are some of the fundamental properties that we utilize to perform quantum computation. Then RSA encryption and some of these particular problems. So basically mechanisms actually certain algorithms pose a threat to such kind of technologies that are currently called as state of the art. We have quantum complexity theory, something very important in quantum computing, and then quantum algorithms, which is nothing but a step-by-step procedure to perform computation on a quantum computer, which has its fundamentals rooted towards the mathematical representation of qubit and multi-qubit systems. In four quadrants of quantum and classical domain, which include classical data, quantum classical data, classical algorithm, classical data, quantum algorithm, quantum data, classical algorithm, and quantum data, quantum algorithm. So I will not go into the details, but these are some of the things that are studied eventually. Again, now artificial intelligence basically is one of those disciplines which talk about, yeah. Any questions?
रिलेशनशिप म्हणून आहे मोहम्मद सुमन सुलेमानी हाय काय आणि निळकंठ पटेल ते काय म्हणते
So artificial intelligence again is one of the most advanced disciplines of computer science, which is actually disrupting a lot many industries these days. Can somebody go on mute, please? Hello?
लोटेस मधलं सर लेटेस्ट म्हणजे काल सरांनी पाठवलेला एक डाटा होता तो ह्याच्यावरती पाठवला
Hello?
एक्सेल वरती पाठवला तो अजून
Rahul Khalate, please mute yourself.
Yeah. So now let's move towards artificial intelligence. We all know how many applications artificial intelligence has across various disciplines. AI is also contributing to a lot of job cuts across the world from past 1.5 years as well as from past 2 decades. So this is basically from MIT open source courseware, one of the definitions, and then we have Wikipedia definitions as well for machine intelligence, which is nothing but artificial intelligence. So I will not go through the definitions, but basically what it again talks about is algorithms enabled by constraints exposed by representations that support mathematical models targeted to thinking, perception, and action. And then all these three things together. If you are talking about developing something for learning, then you have supervised, unsupervised, semi-supervised, self-supervised machine learning algorithms. Then you have reinforcement learning, which talks about learning from actions. And all these things have a deep-rooted, I would say, deeply rooted. These things are very deeply rooted into mathematics, statistics, and associated disciplines. So this is from taken from ISO standard. Basically, ISO is International Standards Organization, IEC JTC 1/SC42, which defines artificial intelligence in a Venn diagram. And you will see that for artificial intelligence, you will see there are various subdisciplines. What at all it includes: inductive artificial intelligence, predictive analysis, business intelligence, okay, then cognitive sciences, statistical processing, unstructured data processing, etc., etc. which again talks about the application of multiple disciplines, either as intradisciplinary, interdisciplinary, or multidisciplinary fields of research. And that is how technology gets evolved. Similarly, we have 4 quadrants defined by International Standards Organization, and their standard ISO IEC JTC 1 SC 32N 2388B. You can find this in standards on IEC. That how you start from data, generate insights, take some decisions and take some actions, and different technologies under big data that are influenced. Similarly, we have different types of analytics where different levels of mathematics and statistics goes into picture. Here it is descriptive statistics, which evolves into diagnostic systems, then predictive analytics systems, then prescriptive analytics and cognitive analytics. And eventually from this to this, there is a huge amount of rule-based artificial intelligence. Okay, then machine learning algorithms and deep learning algorithms that are getting applied to develop such systems. Then there are definitions of machine learning and deep learning, which I will not go in depth, but it is a scientific study of algorithms and statistical models that computer systems use to effectively perform a specific task. So which again, I would emphasize on statistical concepts. Once you use deep neural network layers for deep, something called as hierarchical or deep structured learning, deep learning, eventually the field becomes more and more complex, and huge amount of supercomputing power is needed to solve using these kind of technologies. Then there are various different types of equations, what humans can infer versus artificial intelligence can infer. But again, artificial intelligence and cognitive sciences both are actually interdisciplinary fields. That's what I wanted to emphasize here. And again, mathematics and statistics is one of the core contributors to artificial intelligence along with computer science. Similarly, we have AI technology landscape, various different types of technologies. I will not go through each of them, but all these type of technologies are something which is an outcome of artificial intelligence systems, and which includes different types of, and here's a couple of examples of YouTube videos I have given, where all these fancy concepts have been used in Hollywood or sci-fi movies. Then different types of AI software. I will not again go into the depth, but I just wanted to show you what are different types of AI software, and then different types of AI software platforms, conversational intelligence platform, that is like Alexa, that is chatbots, intelligent chatbots, video bots, etc. Machine learning software, deep learning software, and then artificial neural networks as connectionist systems and how they are used in different types of applications. Again, backpropagation algorithm. Again, there is a lot of mathematics that we can see here. Basically, here is a partial derivative that is going into for the chain rule, etc. Basically, so we can understand that most of these things are heavily dependent on mathematics and statistics. And then this is basically a mostly complete chart of different types of neural network architectures, which I will not go in depth. Yeah. Coming back to quantum and AI together, this is a particular slide which talks about which all disciplines actually go into making of quantum machine learning as a discipline. And just for the sake of understanding, I'm just keeping it here as it is. And then definition of quantum machine learning is that it integrates quantum algorithms with machine learning programs. And how it does it is, I will not go into the details considering the time limit basically. So we have, I will quickly cover. So quantum technology applications and challenges. What are different technologies and how we solve different types of challenges related to that. This is again related to challenges. I will not go here. Emerging trends in quantum technology applications. This also has AI. All these fields also has AI applications. So quantum machine learning, quantum natural language processing, quantum natural language understanding, quantum internet, that is 6G, quantum key distribution, quantum cryptography, for data security. 6G is something which is recently implemented nationwide by Japan, and 6G, to implement 6G, you need quantum machine learning. Then quantum computing for finance, then quantum computing for healthcare, advanced research, and space communications and research and technology as well. And then we will not code right now in this session, but what all mathematics goes in the background, basic state, pure states, and mixed states to explain from quantum perspective, you need to understand the respective mathematics. This is again how to represent it, a detailed slide. Then you have to actually how a pure state matrix is constructed. So definitely there is a contribution of mathematics here, and then different types of matrices that are used, especially for quantum computation, which is mentioned in this particular diagram, which is famous called as Russian doll's map of matrices. Again, one more concept that I just wanted to highlight is about Fourier transforms. Almost all of the quantum algorithms that are used today have a module of inverse quantum Fourier transform, and phase estimation uses inverse quantum Fourier transform as a module, and phase estimation module is used by Shor's algorithm, for which Peter Shor got a Nobel Prize a couple of years back. So this is taken from a basic YouTube video where how from a signal this is complex domain representation and then transform, which is Fourier transform, and then how this is the guy who got the Nobel Prize, and you can see that this is the quantum circuit basically for Peter Shor's algorithm, which does integer factorization much quicker as compared to the other classical counterparts. And this is where I would like to stop. And I can also show you some after the question and answers, the file that contains the billion-digit approximation of pi and one quantum program. In due interest of time, I will not run it, but I will just show you a quantum program to calculate the value of pi, which is the irrational number, which is the ratio of the circumference to the diameter of a circle. And this covers my content today, and I would be more than happy to answer questions and answers. So quantum, artificial intelligence, algorithms and applications related to all these fields and respective role of mathematics was my intent to be covered today. And please feel free to ask questions. In one of the NASA Quantum AI Laboratory talk in Google Symposium 2022 on quantum computing, the director of NASA Quantum AI Laboratory actually talked about this particular sentence as his conclusive statement of the talk. And I would also like to utilize and reutilize and copy this from his session, where he said that the best way to know what is going on in these emerging and next generation technology disciplines and industry fields is to follow the research and not the press release, because Google and NASA also press released that they achieved quantum supremacy, but when it was evaluated, they figured out that no, they did not achieve quantum supremacy. And that's why going through a rigorous work of research and product development is the path forward to develop and utilize these technologies for our nation and for the mankind. So with these 2 cents, I would conclude my talk and will open the forum for questions and answers.
Himanshu sir, there is, I think, one question in chat box.
Right. Quantum cryptography is kind of a threat to quantum computing world, can be solved doing quantum computing. How sounds trivial. So quantum cryptography is a solution for the threat posed by quantum algorithms. Quantum cryptography is encoding something. Cryptography is a discipline of mathematics which talks about encoding things. Okay, so if you have some data, for example, I encrypt my password before storing it into the database in such a manner that nobody will be able to decrypt it. This has been used, and there are different ways and methods of encrypting data which are studied in the field of mathematics called as cryptography. Now, because most of these methods can be actually hacked by quantum algorithms, But today we do not have a mainstream large-scale quantum computer. That's why it is still not a threat. But let's say 5 years down the line, we have a million qubit quantum computer. It can break any RSA encryption across the world. And that's why quantum algorithms are a threat to secure data security. And post-quantum cryptography is the solution to that. So as quantum algorithms is a threat, there are algorithms and protocols that fall under quantum communication and quantum cryptography called as post-quantum cryptography. Some of them are based on quantum key distribution protocol. And if you utilize them, then they actually do encryption in such a manner that even the best quantum algorithm will never be able to break it. And why is it so? So then you will have to go in depth into what is quantum key distribution protocol. It uses some fundamental properties of subatomic scale universe called as entanglement and superposition in such a manner that nobody will be ever able to actually break a secured system. Okay, so I will not go into the depth, but let me know if I have answered your question, Nitin. Perfect, thanks. Okay. Any other questions? So what I will do is, and again, I just wanted to highlight you that how important is quantum computing and quantum artificial intelligence is basically there. This is, I think, 2 years back, by the way, but there is huge investment happening in the field of quantum computing in billions of dollars. Multiple governments across the world are actually investing. There is huge market potential of quantum applications software, and these are different industries like finance, life sciences, aerospace and defense, chemicals, then TTL, which is transport and logistics and travel, and then automotive and assembly, and EPNG, which is electric power and natural gas. All these industries, what type of application of quantum and AI is done is actually mentioned in this particular part of this slide. And I would like to show you.
Himanshu sir,
Yes, yes.
there are several queries in the chat box. They are wanting your contact number as well as your email ID. And if you are comfortable, you can please share
Sorry?
your email.
Your voice is breaking, Nazir. Hello? Yeah.
Hello.
Can you please repeat once again?
Hello. Yes, sir.
Now it is much better. Yeah.
There is some query in the chat box regarding your contact number or email ID.
Yeah, sure.
Please
So,
you can share the same.
So this year, I myself and another founder director, we both have found eQspanse NextGen Technologies. It is the first quantum and AI software platform, product and solutions company in India, private limited company. And we are developing our own quantum enhanced AI platform from scratch from past 1.5 years. And we are targeting space technology and deep tech domains, although not limited to only aerospace, defense, and space tech, but to medical R&D, pharmaceuticals, healthcare, as well as banking and finance, insurance and retail sectors as well, including mining and oil and gas. So you can check and you can get the contact details on our website, that is www.eqspanse.com. We also exist on LinkedIn. And this is our LinkedIn page. I will just show you. So this is our LinkedIn page. So I will paste the link for that as well.
Yes, sir, exactly. We receive your website as well. Yes, link as well.
Sorry?
We have received your website as well on the in the chat box.
Perfect. So yeah, awesome. So you will also in the chat box, I will also paste our LinkedIn page. And both of our email IDs as well as our contact details are on our website as well, so you can reach. And we have our office in Amanora 116 Amanora Apex Business Center
सॉरी कर रहे
in
हैं
Pune.
मुझे पता है आप कितना सीधा बोलती है बहुत सीधे हो मैडम आप
Uh, So you can visit our office anytime. Okay, we have multiple offerings. We are developing our own platform, and we also have different services. We usually develop software in data science, data engineering, IoT, and artificial intelligence and quantum software development. So, and quantum enhanced different types of technologies, all these technologies. So quantum enhanced AI, quantum enhanced IoT, quantum enhanced data engineering and data science as well, Nazir. I hope I answered your question, Nazir.
Oh, sir. Thank you very much. Thank you very much, sir.
Thank you,
Because,
Nazir.
okay, sir. This is
Uh,
Dr. Nadeem from Mathematics Department. Have you concluded, sir? Can I proceed further?
Sorry, yeah, you have any questions? Yeah, please go ahead.
Himanshu sir.
Thank you very much,
Thank
sir.
you, thank you, Nazir, sir. Yeah.
Himanshu sir.
Yeah.
Okay, sir.
There
Yes,
is one
Mahesh.
question
Mahesh,
in
sir.
chat box. In
Yeah,
which
yeah.
topic data science with AI and machine learning used for research? Like that question is there.
Which topic data science with AI and machine learning used for research? Okay, so there are multiple use cases. Okay, I will not go in depth into that, but we are working on different types of such use cases, and I will quickly show you our use cases. Um, So if you see, typically doing planetary weather prediction, just a second. So geospatial phenomenon, critical events related to our planetary atmosphere, etc. These are some of the use cases. Then accurate detection of 2D, 3D patterns, UFOs, object detection, military surveillance, there is an application. Then like national defense and security, planetary defense and security. Geospatial exploration, there is application of quantum sensors and quantum AI, where you can, if you want to detect what is beneath the ground, like water, minerals, heavy elements, oil reserves. So oil and gas mining, multiple industries are onto it. And Australia is very much ahead in this particular area. Then medical diagnostics for precision medicine is the use case. For example, cancer. We usually get cancer detected in the 3rd or 4th stage, which is very late, when you cannot save the life of a person. But if it gets detected in stage 1 or 2, for which you need data and a lot of patterns for the diagnostics of such critical illnesses. This is one of the use case. Then drug discovery is another use case, where this is the first application, by the way, in drug discovery, where people have worked on developing molecules for different types of diseases. And again, genetic sequence imaging, genome sequence imaging is another application. Diagnostics and prognostics, Rolls-Royce, BMW, Mercedes-Benz, all are implementing quantum and quantum AI algorithms to identify the life of their batteries, to identify the life of their engines and automated cars, etc. So lot many systems, simulation of complex systems, all these are use cases for quantum simulation, quantum machine learning, and quantum AI. And then there are some of the hybrid quantum systems for business applications where we specifically specialize. These are different types of algorithms that we develop and embed it in our platform. This is our prior experience. So I hope I was able to answer your question, sir.
Nazir sir.
Yes, sir. Yes, sir.
Okay. So Himanshu sir, now I request Dr. Nazir sir to give vote of thanks.
Thank you, sir. I will
Thank you
mute
very much,
myself.
sir. Himanshu Vaidya, sir, for this
Thank you.
wonderful session. It was really a great and effective session, almost for every subject in science and technology, and especially for our mathematics community. Thanks to Chancellor, Sir Harshvardhan Patil, Executive Director, Dr. Girish Sai, sir, Vice Chancellor, Ma'am, Dr. Manimalpuri, Ma'am, Pro Vice Chancellor Dr. Sudeep Thegde sir and HOD sir Dr. R.G. Viradar for their kind support for organizing this event. And I'm highly thankful to the organizing committee as well. Professor Mahesh Jagtap sir, Professor Prerna Jain ma'am, Professor Amol Dhole sir, and Professor Arvind Kumar Sharma ji. Thanks to each and everyone joining us today's insightful session. Last but not the least, thanks once again, Mr. Himanshu Vaidya sir, for this wonderful session. And we hope in near future we will listen you offline as well in our campus. Thank you very much. Thank you, sir.
Thanks a lot, sir. Thanks a lot, sir. Thank you, Mahesh Jagtap, sir. And
Thank you, Himanshu sir.
Thank you,
आज
Pimpri.
आपल्याला जायचा विचार नाही असं वाटतंय.